Okay, so let's talk about Lewis structures. So when it comes to atoms, the Lewis structure is basically a very simple representation which shows you only the number of valence electrons for that particular atom. Now remember, the valence electrons are those electrons that are in the highest energy level or the outermost shell. So for example, in the case of sodium, it has only one valence electron. All right. In the case of fluorine, it has 7 valence electrons. Okay, so in the Lewis structure representation, basically what we do is that we write down the symbol for the elements and then we put dots around it to represent the valence electrons. So for example, boron has 3 valence electrons, right? So therefore we put 3 dots around it, as you can see here. And that basically is the Lewis structure or the Lewis symbol for boron. And let me just say here that it doesn't matter how the dots are distributed. So you can have, for example, as you can see here, 2 dots here and 1 dot here, but I could have just as well moved one of these dots over here, and or I could move one of these dots down here. It doesn't really matter how the dots are distributed around the symbol. As long as you have the correct number of dots, that's sufficient as far as the Lewis symbol is concerned. All right. Um, of course, we get the valence electrons from the fact that we have 2 electrons here in the case of boron in the 2s orbital and 1 electron in the 2p orbital, and these orbitals are from the second shell, which is the valence shell. All right. Okay. Now, in some textbooks, they make a big deal about pairing the electrons. To be perfectly honest, it's not absolutely necessary when it comes to the Lewis symbols. Most often, we are not concerned with how the electrons are paired. We just put the electrons around it in any way you prefer, and that's it. All right. Okay, so that's basically the Lewis symbol of boron, and you can determine the Lewis symbols of other elements such as sulfur. As you can see here, this is the Lewis symbol for sulfur. 6 electrons around, or 6 dots around the symbol for S, representing the 6 electrons. All right. And this is basically a table giving you the Lewis symbols for elements up to the 20th element, calcium. All right. And you see a trend emerging where, of course, the number of dots is basically equal to the group numbers. So as you can see, for example, in the case of nitrogen and phosphorus, 5 dots around each symbol, and they both belong to group 5A. All right. So again, we see the relationship between the position of the element in the periodic table, or specifically in the group, and the number of valence electrons that is present for the atom of those elements. Okay, so what we're going to do now is talk about the type of bonding that occurs between atoms. The first type is ionic, and the second type is covalent. So we're going to deal with the ionic bond first, and then the next video will be dealing with the covalent bond. So in the formation of ionic bonding, what happens is that you have the transfer of electrons from one atom to another. All right. And basically, this happens in most cases so that these atoms will have the same outer electron structure as a noble gas element. All right. Now, when it comes to metals, we saw earlier that they tend to lose electrons, and when they lose electrons, they form positive ions known as cations. Nonmetals, on the other hand, they form negative ions known as anions. And in either case, whether a cation or an anion is formed, the result is most often a situation where a stable valence electron structure is obtained. In other words, the cation or the anion will have the same electron arrangement as a group 8 element. All right. Now, this structure very often consists of a situation where we have 2 s orbitals and 6 p electrons, or I should say 2 s electrons and 6 p electrons in the outermost shell, right? And we end up with this arrangement by either losing, gaining, or sharing electrons. Now, the losing and gaining will take place in the formation of ionic compounds. The sharing of electrons will occur when we look at the formation of covalent compounds, which would be the subject of the next video. All right. Now, with the exception of helium, This structure consists of 8 electrons in the outermost energy level. So whenever you have electrons being shared or lost or gained, the result would be an electron arrangement similar to elements in group 8, which have 8 electrons on the outermost shell. And here we have the 8 group 8 elements and their electron configurations. The only element in this group that does not have 8 electrons on its outermost shell is helium, and that's because there are only 2 electrons, and those 2 electrons will be in the first shell, and there are no other orbitals within that first shell, so therefore the maximum number of electrons that helium will have is 2. But for the other elements, neon, argon, krypton, xenon, and radon, you'll notice that in the outermost shell you have an S2P6 arrangement where the total number of electrons in the valence shell is 8. Now, let's look at how the sodium atom forms a sodium ion. So the sodium atom has this electron configuration, has a total of 11 electrons and 11 protons residing in the nucleus. So what happens is that the sodium will lose the valence electron here, the electron in the 3s orbital, and when that happens, the sodium atom becomes a sodium ion. And if you look at the electron configuration of the sodium ion, it is the same as the electron configuration of neon. All right? And that's what happens. The electron is lost, and the result would be the sodium ion, and you'll notice that the sodium ion has now 1 fewer electrons compared to the number of protons, and therefore will have an overall plus charge. All right? So that's what happens in the case of sodium. Sodium will lose 1 electron from the 3s orbital to form an electron configuration which is the same as neon and therefore very stable, and the resulting ion will have a plus 1 charge. All right? Okay, here's another example. Now in this case we're talking about a nonmetal, chlorine, which will gain an electron. Now here is the electron configuration of chlorine, right? So when it gains an electron, the 1 electron here will go into the 3p orbital. The 3p orbital in the chlorine atom has 5 electrons, right? But it will gain 1 electron to form 3p6. All right, so now this electron configuration will be the same as argon, right? You'll notice also that the chlorine, or I should say the chloride ion, will have 1 more electron than proton, and therefore will have an overall negative charge. All right? So that's basically how the chloride ion is formed. So when the sodium and the chloride comes together to form a compound, basically what happens is that the sodium loses an electron, and that electron is transferred to the chlorine atom, and then you end up with the sodium chloride ion compound being formed. So the electron that is lost, as we said before, is lost from the 3s orbital, and it is transferred into the 3p orbital of the chlorine atom. All right, so that is what is being shown here. Here you see the electron transfer, and you end up with the chloride ion being formed. And as a result of the fact that the sodium has a plus charge, the chloride has an chloride has a negative charge, then there's going to be a force of attraction between the sodium and the chloride, and that force of attraction is called the ionic bond. All right? So this is basically what happens in the formation of sodium chloride. And basically this is what happens in the formation of any ionic compound that is formed between a metal and a nonmetal. So this is the Lewis representation. This is the Lewis symbol for sodium. This is the Lewis symbol for the chloride or the chlorine atom. You have the electron transfer from the sodium to the chloride, and you end up with sodium with a plus charge and a chloride with a negative charge, and they combine to form sodium chloride. Okay, we can also use the same rationalization to understand what happens when magnesium chloride is formed. So here is magnesium, 12 protons, 12 electrons, and in this case magnesium has an electron configuration of 1s2 when it's not here. But in any case, what happens is that the magnesium will lose 2 electrons, because in the case of magnesium, you're going to have 2 electrons in its outermost shell, and those 2 electrons will be transferred to the 2 chlorine atoms. So each chlorine atom will gain 1 electron, and therefore you're going to end up with the magnesium 2 plus ion being formed, as well as 2 chloride ions, and they will come together to form the magnesium chloride. So as stated down here, the 2 s electrons from the 3s orbital will be transferred to the 3p orbitals of the 2 chlorine atoms. And that's how you end up with magnesium chloride being formed. And you'll notice that the ratio between the magnesium and chloride ions is a 1:2 ratio, all right, as a result. Okay, and again, the attractive force between the ions of opposite charges would be the ionic bonds. Now, in terms of the growth structure of ionic compounds, what you'll find is that they assemble themselves into a regular structure. In most textbooks, they call them a crystal structure. This is what you see here in the case of sodium chloride. So what you have basically is a repeating unit where you have the same arrangement repeated right throughout the entire structure of the particular ionic compound. The result in the case of sodium chloride is that the 1:1 ratio is still maintained. And this is important. This is one big difference between ionic compounds and covalent compounds. There are no discrete NaCl units where you have one Na and one Cl combined together to form one unit. Instead, what you have, as I said before, is this regular arrangement, but the ratio is a 1:1 ratio between the sodium and the chloride ion. All right. So this is basically showing you the arrangement. This is a more realistic representation, which shows you the relative sizes of the ions. But it's the same arrangement as you see in this structure right here. This is just showing you exactly how the ions are placed relative to each other. All right. But as I said before, there's a 1:1 ratio that is maintained. So if you count up all the sodiums and all the chloride ions in this unit right here, you're going to see it's going to be a 1:1 ratio between the sodium and chloride ions, right? Specific to the arrangement in the case of sodium chloride, what you'll find is that each sodium ion is surrounded by 6 chloride ions. And the same is true when you look at the chloride ions. Each of them will be surrounded by 6 sodium ions. All right, so this is the chloride ion. This is a sodium ion right here. So that's showing you the arrangement. So as I said before, the ratio is 1:1. There's no molecule, no discrete unit of NaCl. That's a big difference between ionic compounds and covalent compounds, right? There are no molecules of ionic compounds. The 1:1 ratio is still maintained. All right. Now, in terms of the relative sizes of the sodium ion to the chloride ion, what you'll find, well, firstly, let me compare the size of the sodium ion to the atom. What you'll find is that when an atom loses an electron, the ion that is formed is smaller compared to the atom from which it is formed, which makes sense because when the atom loses an electron, it's going to lose a valence electron. So the number of electrons will be decreased, but the number of protons will still be the same. And therefore, the protons will have a greater attraction for the surrounding electrons, and therefore, as a result, the ionic size will be smaller. On the other hand, so that's what I was just stating here. The sodium atom loses its outermost electron, and as a result, the remaining electrons will now be drawn closer to the nucleus because the nucleus still has the same number of protons. All right, so that explains why the sodium ion is smaller compared to the sodium atom. On the other hand, when it comes to comparing the size of the chlorine atom to the chloride ion, remember, to get from the atom to the ion, in the case of chlorine, an electron is added, right? So basically, you're going to end up now in the ion with 18 electrons, but you're still going to have 17 protons. So as a result, a couple of things will happen. The nuclear attraction for each electron will decrease, and therefore, the size of the ion will increase. In addition, when you add an electron to an atom, you are increasing the amount of repulsive forces between the electrons. So therefore, that also adds to the increase in the size of the anion compared to the atom. All right? Okay. Now, when it comes to formation of ionic compounds, what you'll find is that metals usually have 1, 2, or 3 electrons in their outermost shell. So therefore, when the metal reacts, it will lose either 1, 2, or 3 electrons, right, depending on the number of electrons in its outermost shell, with the aim of obtaining or attaining the electron structure of a noble gas. And consequently, it will become a positive ion. And as I said before, the positive ion, when you look at its size, will be smaller compared to the size of the atom from which it is formed. So typically that's how metals behave when they lose electrons from their outermost shell. Non-metals, on the other hand, tend to have 5, 6, or 7 electrons on their outer shell. So therefore, they will tend to gain electrons, again, gain 1, 2, or 3 electrons, depending on how many electrons that they have in their outermost shell. The aim, of course, is to obtain 8 electrons in its outer shell, and as a result will form a negative ion. And as we described before, the anion, the negative ion that is formed, will be larger in size compared to the atom from which it is formed. All right? So this is just giving you some data about the atomic sizes and their corresponding ionic sizes. So the trend that I just described will be observed here. So if you compare the sizes of the metal atoms and compare the size of the cations formed from these atoms, you'll see that there's a decrease in size in every case without exception. On the other hand, if you look at the size of the atomic radius of non-metallic atoms and compare that to the size of their ions, you're going to see an increase in size in every single case, again, without exception. All right? So that's another observation that you can take note of when it comes to the formation of ions and their atomic sizes compared to the atoms from which they are formed. Okay, how do we predict, I should say, the formulas of ionic compounds? Well, in almost all stable compounds, basically the aim for each atom is to attain a noble gas configuration. So as we said before, metals will tend to lose electrons to gain this configuration, while nonmetals will tend to gain electrons. So if we look at, for example, the reaction between barium and sulfur, this is the electronic configuration of barium, this is the electronic configuration of sulfur. They're both abbreviated electron configuration. So as you can see here, barium has 2 electrons on its outer shell, sulfur has 6 electrons on its outer shell. So we all know what's going to happen. The barium is going to lose 2 electrons to the sulfur. The barium will end up with a xenon configuration, right? And the sulfur will gain the 2 electrons from the barium and ends up with an argon configuration, all right? And the result will be the formation of barium sulfide. The barium is going to end up with a +2 charge, and the sulfide is going to end up with a -2 charge, all right? So that's a relatively simple example, but of course, as you can imagine, things become more complicated with other structures. But before we get to that, let's look at this statement here. Now, it says here, because of similar electron structures, elements from a family or group generally form compounds with the same atomic ratios. So if you think about it, this makes sense, because elements from the same group have the same number of valence electrons, and therefore they tend to form ions of the same charge, and therefore they tend to combine with other elements to form compounds with similar looking formulas. So for example, in the case of sodium, when you look at the oxides of sodium, in other words, or if you look at, I should say, the group 1 elements, right? They all have 1 electron on their outermost shell. When you look at the oxides of these elements, you see a similarities here, right? For every one of these compounds, there are 2 cations for every oxide ion, right? That's true for lithium, sodium, potassium, rubidium, and cesium, all right? You see a similar pattern when it comes to the chlorides. You see a similar pattern when it comes to the bromides, and also with the sulfates, all right? So the point here is that compounds belonging to the same group, they tend to form similar compounds in terms of their formulas and makeup, all right? Okay, now this is reminding you of something that we talked about before. Remember, we said that the group numbers are equal to the number of electrons total in the valence or outermost shells, all right, of the atom, all right? And it is on this basis why we can make certain predictions as to the formulas of ionic compounds that these elements will form, All right. So in the case of sodium chloride, there's a 1-to-1 ratio because sodium has one electron in its outermost shell. So there's a 1-to-1 ratio between the sodium and chloride ion. And that is true not only of sodium, but also of every element in group 1. All the alkali metals, lithium, sodium, potassium, will form chlorides where there's a 1-to-1 ratio between the metal ion and the chloride ion. So they all have similar formulas as you can see here. All right. When it comes to nonmetals, you see something kind of similar. In the case of nonmetals, they will combine according to the group numbers. Now, this is a bit of a jumping of the gun because we're talking about covalent compounds, which will be the subject of the next video. But for now, let's look at what happens in the case of ammonia. Ammonia forms a compound with hydrogen known as ammonia, or I should say nitrogen forms a compound with hydrogen known as ammonia. The formula is NH3, nitrogen's in group 5A, and what you'll find is that other elements in group 5A form similar types of compounds with hydrogens, as you can see here. All right. Okay, we're going to stop here, and the next video will deal with the covalent bond. Until next time.